Good morning, everyone. Yeah, my name is Ben Bussey, Chief Scientist for Intuitive Machines. Very much appreciate the opportunity from the organizers to come and give you an overview of our recent IM-1 mission. And because I wouldn't want to listen to myself first in the morning, I've got like 3 highlights at the beginning, and then you can look back at your phones. So sort of 3 key takeaways where I think things are different from now than when we were in Padua last year is that, this is real now. CLIPS is real. You have the opportunity to have your payloads flown to the lunar surface or dropped off in lunar orbit. This is an image of our Odysseus lander, about 4 meters tall. This was taken just before it shipped to the Cape. So yeah, so note to self 1, this is now real. Note to self 2 is you're going to get bored with this. It's like right now it's all super exciting. Oh, something's going to the moon. I think in 3 or 4 years' time, you might get 30 seconds in the news like, oh, they sent another one. So the point being that the plan is for a regular cadence of deliveries, and I think that's important because realizing that you don't just have 1 or 2 chances in your career to do a flight experiment, and that you can actually fly something, learn from it, desperately apply for funding, and then try and fly an improved version a few years later. The other key takeaway from this slide is the fact that even from the beginning, as you know, NASA set up the CLIPS program. The goal wasn't just to fly NASA payloads. It was to try and grow an ecosystem for delivery of payloads to where NASA was, an anchor customer. But the goal is ideally to get what you see here as IMC-1, which is IM Commercial 1, which would be a mission to the moon where there weren't any NASA payloads. And so they're not that, even though it says commercial, that's a range of institutions. It could be universities, it could even be other space agencies, or it can be technology from industry. The third thing I wanted to point out before I then focus really on IM-1 is we do hear a lot that, well, CLIPS is only about putting 100 kilograms on the moon. And I think it's important to realize that Intuitive Machines, as well as other providers, we're engineering companies. We can build landers of whatever scale, and we can fly to the moon what you want flown. So yes, the Nova C is about 130 kilograms to anywhere on the lunar surface. But then we have a derivative, the Nova D, which can take anything up to 2,500 kilograms, and then after that you go even more into the Roman alphabet to Nova M and take very large payloads. One thing between this year and next, this year and next year, I think I'm especially excited by the flying of the Intuitive Machines Hopper and what that represents to this community and what they can think about doing. So the Hopper, you can think of it as a mini version of the Nova C. It gets flown to the moon by the Nova C, and then it can carry about 8 kilograms of payloads, about 25 kilometers. And it's been designed, if you like, to complement rovers, in that there are certain data sets for which a rover is perfect, and there are some data sets for which a rover isn't optimal, or in fact, a rover cannot do it at all. And so we've really looked here at the extreme access, in that the Hopper can go to places like, the original idea was to go into one of those pits that we see in the Mare and explore inside. For our first mission, we were going to the Shepton Ridge region, where we will do 5 hops, including going into a small permanently shadowed crater, taking a measurement and hopping out. And we're flying a neutron spectrometer from Pulley Water System, Pulley Space Technologies, called the Pulley Water Snifter, which is a neutron spectrometer, which will get the first direct measurement of the surface. Hydrogen, sorry. We're also one of the 3 teams doing Lunar terrain vehicle. Our concept involves having the main rover, if you like, is optimized to be exactly that, to be the rover for the crew. And then we are looking at a trailer mechanism, a trailer architecture, where you could imagine a scenario where you could have a science trailer, depending on what you want to do, or a resource prospecting trailer, or even sort of a resource extraction trailer. Okay, so on to IM-1, which happened in February of this year. So here you can see there was a variety of NASA payloads as well as commercial payloads. And I won't take up the time reading through these. Tim Crane, our Chief Technology Officer, is giving a talk tonight at the public event, and we'll go into some of this better and in more detail. I'm going to talk about the development of the lander and then all the different phases that occurred. So really, as a company, it's sort of, you had to become a mini space agency. It was the development of an entire space program to produce the lander. The middle image here shows Odysseus just before the fairing got closed on the Falcon 9. So the last time we were going to see it. I think one of the key developments was the liquid oxygen methane engine, our VR900 engine. We're fortunate that we were able to build a facility in Houston where we can actually hot fire the engine every day. So we have this building with no roof and incredibly thick walls that we can test the engine throughout an entire mission profile. So we had a really good gauge on how it was going to perform. So this just shows the different parts of the mission all the way from launch to landing. And I've got some imagery to share and some of the highlights of what we learned and the important milestones for us during the entire mission. So launch and transit, those of you that have worked on missions, you always worry, you can model everything, but you always worry. The Falcon 9, any launch vehicle is an interesting environment. And so for nothing to fall off and to continue working afterwards was not insignificant. Also our tank, one of the highlights of the Nova C was our linerless tanks, which allowed them to be the exact size that we wanted, as well as the mass is much lighter. So that we launched down from in Florida, early morning, about 1 a.m. launch. It was stunning. The middle image shows Odysseus, six-legged lander, just departing the upper stage from the Falcon 9, and then in return we took a picture of the upper stage leaving, which is the image on the right. You'll notice that we have two types of camera on the lander. One of them is sort of 170-degree fisheye lens, in case you're wondering why. Like a lot of the images I'm going to show you will look like the one on the right. This is just an image just as we were leaving Earth. One of the reasons for showing this is people have noticed the Columbia logo on the helium tank, and it's important to point out that this wasn't just marketing for Columbia. To say, hey, we've put our sticker on a lunar lander. This was actually a technology collaboration between the two companies, in that we were aware of the material they use in the coats that you might own, and if you don't, you should. No, I shouldn't say that. But also they were very interested to see how that material. I was fortunate enough to meet their chief material scientist, and they liked the idea of sending material to the moon to see how well it worked, because you can't test that on Earth. And so we actually did fly the material that they use in their coats, and they're looking at it from a clothing perspective, and we're looking at it as potentially actively feeding it into our thermal management system if it's an improved material going forward. This is one of Australia, just as we were en route to the moon. One of our thing, we decided early on that we didn't want to rely on Deep Space Network, not because Deep Space Network isn't amazing, it's because it's incredibly amazing and we know it's going to be oversubscribed. And so what we did is we've essentially built our own a global lunar data network, and we've collaborated and have agreements with radio science dishes around the world that we use for ground stations. And so the bottom right, these vary from about 18 meters all the way up to the 64-meter Parkes dish near Canberra in Australia, which is a very nice dish for receiving data. Can you hit? Oh, it worked. Yeah, so this is, this is just a quick movie taken this was as we were entering, or we were in lunar orbit just before landing, and I don't know if I can play again. Oh, it did. Oh, no, sorry. Yeah. You can actually see one of the Rolls' antennas had deployed early. It's a different that can be a Tim story this evening, and you can see that flapping in the wind, so to speak. Just one during descent, one very close to landing. Point out the friendly-looking crater in the top left of the image. You'll be seeing more of that shortly. Again, the landing is often talked about. It was a successful soft landing. Was it perfect? No. However, the spacecraft was intact afterwards, and I think what often gets forgotten is that it operated for longer than intended, for more than 144 hours successfully on the lunar surface, sending back data from all the instruments. So this is quite a sporty picture, just showing the exact moment of impact. Touchdown, sorry. Yeah. Yeah. All good things, all good things. So thanks to this is unfortunately I don't have the animated GIF, makes it easier to see. This is just shows Odysseus on the surface in the left-hand image. It's either a laser or I'm going to turn it off. Either way, you win, which is there. Essentially, the problem that you may have read about is that we had a problem with the connectivity to our laser altimeter, and that affected final approach. So we did in fact land about 2.5 kilometers short of intended. We were on the planned trajectory, but we ended up just landing slightly short, which meant instead of landing up here, we ended up landing just inside that unfriendly crater I pointed out in the previous image. So we landed on about a 12-degree slope, which wasn't planned. So data, so yes, we got just over 500 megabytes of data back from the surface, including from all the payloads, and because I can sense the presence. So then that was so last year. So this is next, and so IM2. Yes, 2. Thank you. Yeah, IM2 is going at the end of this year. We'll be flying NASA the Prime 1. I know Jackie's here today. So that's the Trident drill and mass spectrometer that will also then be flying on the Viper rover. We're flying on Micronova. We're excited to be dropping off the Trailblazer spacecraft in lunar orbit en route. And then we also have a Lunar Outpost rover with a Nokia LTE network experiment, which was another Space Technology Mission Directorate development, just like our Hopper. And then you can also see the range of commercial payloads. And I will stop there, hoping that no one really has a question. There you go.
Thank you so much. Very inspiring. We do have time for a short question. Over there.
It's not Mahesh. But Mahesh was just being polite because no one else had asked.
Good morning, Francesco Latini from Italian Space Agency. So first of all, congratulations on the mission and on the success. Regarding the next one, since you said that the landing on a 12-degree slope was not expected, are there any changes in the future lander to accommodate potential, landing on different slopes?
No, I think the lander is sort of designed to cope with roughly 10-degree slopes. And what happened with IM1 is not only was it a 12-degree slope, but we also had some lateral movement because of the lack of feedback from the laser altimeter. So we're actually, we've learned a lot from IM1 and actually quite happy with our design, that we think that had the laser altimeter been connected, we would have gone to the region. We had a good landing site prepped out where all the slopes were less 10 degrees. We've done the same thing with IM2 on the Shackleton connecting ridge, in that we have a landing region which we know we will land within, all of which that we're happy with the slopes and roughness, etc. And we have confidence in the vehicle that, barring something fairly extreme like that, that we will go where we're intending to fly.